Je pars pour Tokyo. Dans ma tête.
Okay, today we'll finish section 1.5, which is on multiplying and dividing radical expressions. And basically, everything we're going to do today is all about rationalizing denominators. You know what a denominator is. It's the bottom number in a fraction. And what we have to do is to rationalize denominators. What does that mean? It means to get rid of any radicals in the denominator. So for example, this first expression has a square root sign in the denominator, and we don't want that there. You don't want to have radical signs in the denominator. So before I teach you how to do this, you're probably wondering, well, why not? What's the big deal about having radical signs in the denominator? So the reason is because at one point in time there were no computers. And so if someone wanted to figure something like this out, 3 divided by root 5, what they'd have to do is they'd have to look up on a table. They had a table for square roots, and they'd look up what the square root of 5 is on the table. So they'd look it up, and what they'd find is that the square root of 5, let's do it to, I don't know, 4 decimal places or something. The square root of 5 is 2.2361. And they want to divide it, to put that into 3. We want to know how many times does that go into 3. Okay? So that's what they could do. Or they could rationalize this. And I'm not going to tell you how to do this yet. I will in a second. But when they rationalize this, they would get root 45 over 5. So what they would have to do is they'd have to look up 45 on their table, square root of 45, and if they did that, they'd find it's 6.7082, and they divide that by 5. Now, you might look at both of those and say, well, what's the big deal? Why is this one, this bottom one, preferable to this one? Well, look how fast I can divide this bottom one. 5 goes into 6 one time, and there's 1 left over. 5 into 17 goes in 3 times. There's 2 left over. 5 into 20 is 4 with none left over. 5 into 8 goes 1 with 3 left over. 5 into 32 goes 6 with 2 left over. Put another 0. 5 into 20 is 4, and the decimal goes straight up. I'm finished. Okay, so there's my answer. This is a nightmare to do this by long division. I don't know if you remember how to do long division when you have decimals like this. You have to move this decimal over 4 spots, so you get 22361. Move this decimal over 4 spots, so you get that, right? Yep. And now I have to ask myself, how many times does 22,361 go into 30,000? I guess 1. And now I have to subtract all that and bring down zeros. It's horrible. I do not want to do that. So this is the reason they rationalized denominators. It made it very, very easy, or much easier, to figure out amounts like this. Now, probably some of you are screaming at your phone or your computer or however you're watching this, saying, yeah, but there's one thing that's pretty different than what you're talking about, Mr. Waj. We have calculators. I know. I've always thought this is a bit ridiculous. But what can I do? I need to teach it to you. It does show up all the time in university and that kind of stuff if you take math courses, and you will be expected to rationalize denominators. So let's teach you how to do it. The good news is it's not too bad. There's basically 3 different types. And the first type is when you have a denominator which is a monomial square root. Okay? And what you're going to do in those cases is you're going to multiply the top and the bottom by the denominator, by whatever the denominator is. So we want to get rid of the square root of 5. What can you multiply the square root of 5 by to get a whole number? You can multiply the square root of 5 by the square root of 5, because the square root of 5 times the square root of 5 is the square root of 5 squared, and that equals 5. What can you multiply the square root of 8 by to get rid of the square root? Multiply it by the square root of 8. Right? Any square root multiplied by itself just leaves you with the whole number. That is what we want. So you're going to multiply this bottom by the square root of 5. But you can't just multiply the bottom and do nothing to the top, otherwise you'd be changing this amount. So you have to do the same thing to the top. You have to multiply that by square root of 5. If we do that, what do we end up with? Well, on the top we get 3 root 5. It's not root 15 because this is not in a radical sign. So you get 3 root 5. On the bottom, root 5 times root 5 equals root 5 squared, or if you want, root 5 times root 5 equals root 25, and the square root of 25 is 5. By now you should be getting this, that root 5 times root 5 equals 5. And we're done. We're finished. Believe it or not, this is a simpler form. We've rationalized the denominator. We are finished. Now, by the way, when I multiplied this root 5 here and this root 5 here, I multiplied by root 5 over root 5. What's that equal to, root 5 over root 5? It equals 1, right? And when you multiply anything by 1, you don't change the amount. So this is kind of like a little proof that this amount that I've circled here is exactly equal to this amount here. It's just a different form, and in this case it's a simpler form because we've rationalized the denominator. Okay, next one, number 2 here, the square root of 5 over 7. So the whole fraction's in a radical sign this time. But remember, if the whole fraction's in a radical sign, you can separate it. You can make it like this. And that's great. Once we've done that, we want to rationalize the denominator. So we look at the denominator, it's a monomial. We just multiply the denominator by root 7, and whatever we do to the bottom, we do to the top. So what are we left with? Root 5 times root 7 is root 35. And root 7 times root 7 is root 49 if you want, but it actually just equals 7. The square root of 49 is 7. Root 7 times root 7 is 7. Now be careful, I know 35 and 7 you can divide, but in this case you can't because they're not both in radical signs. If they're both in radical signs you could, but there's nothing you can do here. You're finished. Okay, third one, the denominator is root 5. We want to get rid of it, so we multiply by root 5, and we have to multiply this whole thing by root 5. In other words, you're going to be doing some mountains here on the top. Okay, on the bottom, let's do the bottom first. Root 5 times root 5 is 5. On the top, 4 root 5 times root 5. So there's like a 1 here, right? So it's 4 times 1 is 4. And root 5 times root 5 is 5. So you're going to end up with 4 times 5 there. And then for the other mountain, we have negative 2 times 1, which is negative 2, and we still have the root 5. Okay, 4 times 5 is 20. Take away 2 root 5, all divided by 5. Finished. Okay, the next ones are monomial. Again, monomials in the denominator, but they're non-square roots. So for example, we have a cube root here. These are difficult, more difficult. Yeah, so again, just like we did up above, if the whole fraction's in a radical sign, why don't we split it up? So we would have the cube root of m over the cube root of 3. Now, people get used to that method we used up above, and they think, okay, what I'm going to do is I'm going to multiply the bottom by the cube root of 3 and do the same to the top. Maybe don't write this down yet, because look what happens here. If I multiply the cube root of 3 times the cube root of 3, I get the cube root of 9. Can you take the cube root of 9? Some of you might be saying, yes, you can. It's 3. No, it's not 3. You're looking for a number that multiplies by itself 3 times and gives you 9. I don't know what that is, but it's certainly not 3. It's 2 point something. We don't want that. So can you figure out what you would multiply this by? You would almost multiply it by this cube root of 3, but not quite. You'd multiply it by the cube root of 3 squared. I'll show you why in a second. What you do to the bottom, you have to do the top. We're going to multiply the top by the cube root of 3 squared as well. Okay, so let's look at the bottom first. Cube root of root 3 times the cube root of 3 squared equals the cube root of, well, if we multiply 3 to the first times 3 squared, we get 3 cubed. Or if you want, you can write out 27. That's what it equals. This is 9, this is 3, you get 27. You can do it that way too. And I'll just continue on the bottom. If you're doing the cube root of 3 cubed, basically what you have inside here is 3 3's. And you can only bring it out if you have a group of 3, because it's cubed, and you do have a group of 3. So what comes out is 3. You're just left with a 3 on the bottom. That makes sense? It's a little bit tricky there. On the top, we have the cube root of m times the cube root of 3 squared. So what you get is 3 squared, which is 9, times m. So you get the cube root of 9m. And I'll just rewrite that here with my final answer. That's it. You cannot simplify that 9. I know you want to make it 3 or something, but the cube root of 9 is not 3. So this is your answer right here. Okay, another one of those ones. Here's one. Do you notice that you have numbers that you can simplify? 7 and 21, you got x's on the top, x's on the bottom. So this is a case where you might want to start by actually writing it as a single radical. So 7x squared over 21x to the 9th. Because once you have the whole thing in a radical, you can simplify it. 7 and 21, if you simplify that, what do you get? You get 1 on top and 3 on the bottom. x squared, x to the ninth. Where do you have more x's? On the bottom. How many more? 7. So you could just write that right there. Great, that's made it a lot easier. Now you could go back and split it into 2. So the fifth root of 1 over the fifth root of 3x to the 7th. What's the fifth root of 1? What's a number you multiply by itself 5 times to get 1? Just 1. So on top all we have is 1. And on the bottom we still have the fifth root of 3x to the 7. Maybe I'll write that again down here. Sorry, this is a long question. So we need to rationalize this denominator. So this is tricky. What are you going to multiply the bottom by so that you can take the fifth root of it? We're not going to multiply by 3 because you'd have 3 times 3 is 9 and you can't take the fifth root of it. You're not going to multiply by 3 squared because that'll just get you up to 3 cubed. How many 3's do you need? You need 4 because 4 plus this 1 will give you the 5 you need to be able to take a fifth root. You already have 7 x's. How many more do you need? 3. That's going to work, as you'll see shortly. Okay, what you do at the bottom, you do the same at the top. So the fifth root of 3 to the 4th x cubed. That's a 4. So let's go ahead and do this. 1 times all this, so this just stays the same. So we get the fifth root of 3 to the 4th power. What is that? 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81 x cubed. And on the bottom what we have is the fifth root of 3 to the 1 times 3 to the 4th is 3 to the 5th, and the x to the 7th times x to the 3rd is x to the 10th. So the top's done, the numerator's done. Fifth root of 81 x cubed. On the bottom, you need a group of 5 to bring it out, and you do have a group of 5. You have 3 5's, so a 3 comes out. You have 10 x's, and you need a group of 5. So how many groups of how many x's come out? 2. There's your answer. That's a very difficult answer. Okay, this is probably more difficult than anything in the homework even. So if you're getting these, you're doing great. Alright, the third type is much more common. I would say B. These ones we just did are not nearly as common. You don't need to know those as much as A and C, but you definitely need to know C, which is when you have a binomial in the denominator. It's a little more work. What you have to do in that case is you're going to multiply the top and the bottom by the conjugate of the denominator. What's a conjugate? Well, it's hard to put in words, but it's easy if I give you an example. 3m plus 2 is the conjugate of 3m minus 2. 2b squared minus 3 is the conjugate of 2b squared plus 3. So you see the conjugate is just exactly the same binomial, except the sign in the middle is different. So if we want to get rid of this radical in the denominator, we're going to multiply by the conjugate of the denominator. So the conjugate of this is exactly the same thing, except instead of minus, it's plus root 3. What we do at the bottom, we also do the top. Okay, on the top, you have to do mountains. So you get 5 times 2 is 10, and 5 times root 3 is 5 root 3. On the bottom, you have to do mountains, and you have to do valleys. 2 times 2 is 4. 2 times root 3 is 2 root 3. Negative root 3 times 2 is negative 2 root 3. Hope that makes sense. You have a 1 here, and 1 times 2, or negative 1 times 2 is negative 2 plus the root 3. And the last one is negative root 3 times positive root 3. Well, negative times a positive is a negative, and root 3 times root 3 is 3. Hopefully you're getting those. Okay, on the top, we have 10 plus 5 root 3. On the bottom, if you take a look at these two middle terms, this will always happen when you have this rationalized in the denominator and you have the binomials. They cancel. You have plus 2 root 3 minus 2 root 3. So those are gone. And what you're left with at the bottom is 4 take away 3, which is 1. Do you need to put anything over 1? No. Dividing by 1 makes no difference. So you can just write it like this. Hey, that's a good answer. Much simpler than this. Last one, number 7. This is a difficult one if I remember. So what we need to do is we need to multiply the bottom, which is a binomial. We have to multiply all that by the conjugate of it. And the conjugate is 5 minus 4 root 2. What we do at the bottom, we also have to do the top. So we have to multiply all that by 5 minus 4 root 2. So you got lots of multiplying to do here because on the top you have to do mountains and valleys, and on the bottom you have to do mountains and valleys. That's getting pretty messy. I think I'm going to take those away. So let's go ahead and do that. on the top, 6 root 3 times 5 is 30 root 3. 6 root 3 times negative 4 root 2 is negative 24 root 6. Root 3 times 5 is 5 root 3, and root 3 times negative 4 root 2 is negative 4 root 6. On the bottom, 5 times 5 is 25. 5 times negative 4 root 2 is negative 20 root 2. 4 root 2 times 5 is plus 20 root 2, and 4 root 2 times negative 4 root 2 is negative 4 times 4 is 16, and root 2 times root 2 is 2. So I'll write it like that. You could also write root 4 if you want, but I'll just go straight to 2. Okay, on the top, is there anything you can combine? Well, we have 30 root 3 and 5 root 3, so that equals 35 root 3. And I have negative 24 root 6, and take away another 4 root 6, so that's negative 28 root 6. On the bottom, it happens again, negative 20 root 2 plus 20 root 2, so those are gone. And I have 25 take away 16 times 2 is 32. So 25 take away 32 is negative 7. Okay, good job. This, if you get to here, you're doing great. Now, if you want to really give me a 100% great answer, here's what you want to do. You need to look at the top here, this binomial, right? There's two terms. I should have talked about this before. And you want to see, is there something you can factor out of both of these coefficients? And there definitely is. The greatest common factor of those coefficients is 7. So you get 7, and what you're left with is 5 root 3 minus 4 root 6. Does that make sense? Divide 35 by 7, you get 5. Divide 28 by 7, you get 4. And that's all over negative 7. Hey, look it. You got a 7 here, you got a negative 7 here. You can cancel those. Except 7 divided by negative 7 is negative 1. So you're just left with negative 1 here. Now, if you want, you could leave it like that, negative 1 and then 5 root 3 minus 4 root 6. But what's even better is if you kind of do the mountains back here, and you'll get negative 5 root 3, and negative times this negative 1 times negative 4 root 6 is plus 4 root 6. That's even better. Or what the best answer of all is, because often in math, when we have a negative and a positive, we put the positive first, 4 root 6, and then take away the 5 root 3. Oh, that's beautiful. I love it. If you can get to that, you've really got it. Hey, if you can get to here, that's good. If you can get to here, that's awesome. And if you get to here, it's, you know, absolutely amazing. But this is great here. I just want to go back and talk about one thing. When you get this answer right here, lots of times people don't want to do the factoring. The other way you can do it, since there's 3 terms, one here, and one on the bottom, if you can divide this, this, and this, you have to be able to divide all 3 by something, you can do it. And you can divide them all by negative 7, or 7 if you want, and they have to deal with the negative. But you could do that. But if I had something like this, 4 root 8 plus 3 root 2 all over 8, could I simplify this? A lot of people try to. They try to cross out this 4 and this 8, make it 1 and 2, but you can't. You have to be able to simplify this, this, and this, all 3 terms. Okay? We'll talk about that a lot in class because people make that mistake all the time. Okay, we're done rationalizing the denominator.